Ultra-fast nano? A solution for quantum computing? No, it doesn't look like this. Electronics at the nanoscale looks very different. But it doesn't look like this either. On a nanoscopic scale, particles are waves and look more like this. These different waves are the secret behind the promise of quantum computing. But they are not very simple to understand. Let's imagine that an electron looks like this.
Hello.
And let's take a closer look at its behavior. In a quantum state, particles have both their heads up and down, but also right, left. Particles are in several states simultaneously. The big challenge to keep this funny behavior is that when other particles interact with it, the electron loses its quantum state. One talks about decoherence. This rule explains the formation of the tangible world as we know it. Thank you all very much. You can take a short break. Now, we have to explain the challenges of quantum computers. Let's consider a computer. As you may know, computers encode their information in a binary basis, meaning in a bunch of zeros and ones. Therefore, on a classical computer, one bit has only two possible states: state 1 or state 0. Not so clear. Let's ask our little friend to come back. Let's say that state 0 is head down and state 1 is head up. A quantum bit could be both 0 and 1 with possible variations. It can be 80% of 1 and 20% of 0, 50-50, 60-40, etc. to infinity. So, in a single qubit, we could encode infinitely more information than in a normal bit. But the problem is that a useful computer needs more than one bit to do any operation. And that's the whole problem with quantum computing. How to maintain the quantum state with multiple qubits? One of the solutions is to fight decoherence through speed. And that's what explores the project Ultra-fast Nano. The project consists in building the first electron quantum bit that moves, more than 100,000 km per hour. At this speed, one cannot see anything. Let's slow it down by 100 billion times. Of course, it doesn't have wings and doesn't move randomly, but inside an electronic device with different sections. Come on, get prepared. An femtosecond laser will launch you. At such speed, we need unprecedentedly fast electronics to control it. In real life, it is a bit different, but you understand the idea. The electron is launched at the junction point. Then, it will slalom between the upper and the lower rail until it is in a superposition of state, simultaneously in both rails. Due to a magnetic field, the upper part of the electron experiences a different dynamics than the lower part. Then, another slalom section recombines the two parts into one. At the end, an ultra-fast detector takes a picture to detect where the electron is. The long-term goal would be to build a circuit with all the sections, switches, like a train circuit. But we are not there yet. The goal is to understand the behavior of electrons at this ultra speed, and this is uncharted territory.